Okay, let's look at our second example. This example, we were again finding orthogonal trajectories. And instead of parabolas, now we have this as our family of curves. What curves are these? These are going to be circles centered at k comma 0 with the radius of k. So let's look at this. So our equation is x minus k squared plus y squared equals k squared, and we're told that k is not equal to 0. So these are circles with a center of k comma 0 and a radius of k. Or actually, I should put absolute value of k for the radius. Okay? And remember, that's just going back to the general formula or the general format for the equation of a circle. X minus h squared plus y minus k squared equals r squared, center h comma k, radius r. Okay? All right. So our first step is going to be, do you remember what the first step is? The first step is to find a differential equation. What differential equation is satisfied by our circles? Right? So our circles, say if k is 1, then the center is 1 comma 0 and it's got a radius of 1. Okay, if k is 1/2, then the center is 1/2 comma 0 and it's got a radius of 1/2. So we have all these circles that are tangent to the y-axis, right? So as you move the center closer in, the radius gets smaller. So it's kind of like bug eyes. Okay. So you've got to find the differential equation satisfied by all of these circles. So step 1 is to find our differential equation. Right, so here we go. Find a differential equation for the given family. And we need to get it to be y prime equals f of xy. And how we're going to do that, again, is we start by taking the derivative of the equation for our curves. So we've got x minus k squared plus y squared equals k squared. Here's the thing. Every time you're going to have to worry about implicit differentiation. So in the last video, we used implicit differentiation because we were taking the derivative with respect to x of k times y squared, so we had to use the chain rule to give us 2y prime. Now, over here, with our implicit differentiation, we're going to take the derivative with respect to x of both sides. So the derivative with respect to x of x minus k squared plus the derivative with respect to x of y squared equals the derivative with respect to x of k squared. Now the right-hand side is going to be easy. That's just going to be equal to 0 because k squared is a constant. Okay? Now, let's see, what about this? If I take the derivative of x minus k squared, I know how to do this. I'm going to use a chain rule, so I have 2 times x minus k. That's it, right? And now what about this derivative of y squared? Again, this is implicit differentiation, so I'm going to have to use the chain rule. And I'll have 2 times y times dy dx. Okay, so adding it all together, I've got 2 times x minus k plus 2y y prime equals 0. Now remember, my goal is to get a general format of y prime equals f of xy. That's my goal. Okay, so let me try to solve for y prime. So I have 2y y prime equals negative 2x minus k. So I'm just subtracting 2 times x minus k. And now I'm dividing by 2y. So I have negative 2x minus k divided by 2y. The 2's cancel out, so I can have y prime equals, and I can distribute that negative, huh? So I have k minus x over y. Am I done? No. Why? Because I need to get rid of that k. Remember, I need a differential equation that does not involve k. It only needs to involve x and y. I look back here and I need to say, what is k in terms of x and y? Well, let's see here. How do I find out my k? I go back to my original equation. So my original equation for my circles says that x minus k quantity squared plus y squared equals k squared. Let me expand the left hand side, so I'll get x squared minus 2xk plus k squared plus y squared equals k squared. The k squareds are going to cancel out, and I'll have x squared minus 2xk plus y squared equals 0. Okay, so I'm going to bring that to the right hand side, so I'll have 2xk equals x squared plus y squared. So now I can solve for k. K is equal to x squared plus y squared over 2x. Okay, so this I'm going to substitute into my differential equation. That's how I'm going to eliminate k. So I'm going to combine these two facts, right? So my y prime is equal to k, but k is equal to x squared plus y squared over 2x minus x over y. Okay? So now this I can simplify as y prime equals, and when I simplify I'll get x squared plus y squared minus 2x squared over 2xy. Okay, so y prime equals x squared y squared minus x squared over 2xy. So this is the result of my step 1. So this is my differential equation. This is the differential equation satisfied by my circles. Step 2, right,
it's
is
9:45.
Thank you. So my f of xy is going to be y squared minus x squared over 2xy. So my next step is going to be to solve my brand new differential equation, right? And how do I get my brand new differential equation? Well, my new differential equation that I'm solving is supposed to be y prime equals negative 1 over f of xy. So I have y prime equals negative 1 over f of xy, which is equal to negative 1 over y squared minus x squared over 2xy. Okay, so y prime equals, and I can rewrite this as 2xy over x squared minus y squared. So my goal now is to solve this diffie q. Guess what? This differential equation is homogeneous. So this diffie-q is homogeneous. And we can use the substitution. Remember, if it's homogeneous, we use a substitution, v equals y over x. So we can use the substitution, v equals y over x, y equals xv. Y prime is going to be x v prime plus v. So our differential equation with our substitution is going to become x v prime plus v equals 2x. Now remember, what is y? Y is x times v. xv over x squared minus xv squared. What have I done? I have replaced y with xv. So instead of y, I have xv. Right? Instead of y squared, I have xv quantity squared. And I've replaced y prime with x v prime plus v. Right? So instead of y prime, I've got x v prime plus v. This is my new differential equation with my substitution. So x v prime plus v equals 2x squared v divided by x squared minus x squared v squared. Okay, let me copy and paste. So let's go ahead and simplify this, because ultimately I'm going to solve for v prime, and then once I solve for v prime, I can back substitute to figure out y. So x v prime is going to equal 2x squared v divided by x squared minus x squared v squared minus v. What did I do? I just subtracted v from both sides. Okay. And now, let's see, I should be able to, simplify. So let's see here. So we'll have 2x squared v minus v times x squared minus x squared v squared all over x squared minus x squared v squared. So we'll have 2x squared v minus x squared v plus x squared v cubed over x squared minus x squared v squared. 2x squared v minus x squared v is going to leave me with x squared v plus x squared v cubed all over x squared minus x squared v squared. I've got a lot of x squareds floating around, so let's pull out x squared and a v in the numerator, and I'll have a 1 plus v squared. And in the denominator, if I pull out x squared, I'll have a 1 minus v squared. My x squareds cancel out, and I've got v, 1 plus v squared, in the numerator, 1 minus v squared in the denominator. So this is a lot of algebra. We are using our algebra skills today. Is this a long problem? Yes. If you keep track of the work that you're doing, you should be just fine. And we need to practice our algebra skills. Okay, so altogether, our differential equation is x v prime equals v times 1 plus v squared divided by 1 minus v squared. Okay? Now, copy, paste. Do you recognize what type of differential equation this is? This is separable. So it is first order, and it is separable. So what do we have? I'm going to separate my variables. On the right-hand side, I'll have 1 over x, and on the left-hand side, I'll have 1 minus v squared over v times 1 plus v squared, v prime. That's totally separable, and I've separated my variables. What am I going to need to do? I'm now going to integrate. So I've got 1 minus v squared over v times 1 plus v squared dv equal to the integral 1 over x dx. The right-hand side is going to be natural log of x plus a constant, right? That's easy. What about the left-hand side? What integration technique do we use? We're going to use partial fraction decomposition. So let's rewrite this as, now with partial fraction decomposition, we're going to be able to rewrite this as the integral of 1 over v minus 2v over v squared plus 1 dv. And this is using partial fraction decomposition. Once we do that, we'll integrate this and we'll get natural log of v, right? Because we have the integral of 1 over v dv minus the integral of 2v over v squared plus 1 dv. So we can do u substitution for this integral right here. Let u equal v squared plus 1. Then du equals 2v dv. So this is going to just be the integral of du over u. So we'll get natural log of u, which is natural log of v squared plus 1. And then the integral of 1 over v dv is just going to be natural log of v. Okay, so we'll have natural log of v, natural log of v minus that. Okay, so putting it all together, we'll have natural log of v minus the natural log of v squared plus 1 equals natural log of x plus a constant. And believe it or not, we can actually combine the left-hand side using our log properties to be natural log of v divided by v squared plus 1 equals natural log of x plus a constant. Now we can exponentiate both sides to get that v over v squared plus 1 is equal to e to the ln x plus a constant. So v over v squared plus 1 equals some constant times x. What was v? Remember v, 3 pages ago, v was actually y over x. So we've got to plug that in. So v is actually y over x squared plus 1 equals a constant times x. So we'll have y over x over y squared over x squared plus 1 equals a constant times x. And we can multiply both sides by x squared. So we multiply the top by x squared and the bottom times x squared. And then we'll have xy in the numerator. And in the denominator, we'll have y squared plus x squared equal to cx. And this is looking like we might actually have some more circles because we can divide both sides by x, right, which is the same as multiplying by 1 over x. So the x and the 1 over x are going to cancel out, right? This x and this 1 over x are going to cancel out. So we'll have, it looks like we will have y over x squared plus y squared equals a constant. And now if we have y over x squared plus y squared equals a constant, multiply, we get c x squared plus cy squared equals y. subtract y, so we'll have cx squared plus cy squared minus y equals 0. Now we can complete the square, right? So pull out the c, we'll have y squared minus 1 over cy plus cx squared equals 0. When we complete the square, let's see here, so cx squared plus a constant times, we have y squared minus 1 over cy plus, so we need to take 1 over c divided by 2 and square it. Should be plus 1 over 4c squared. So I believe that will give us y minus 1 over 2c squared. But if I add c times 1 over 4c squared to the right-hand side, I have to add c times 1 over 4c squared to the left-hand side. So now I'm going to get 1 over 4c on the left-hand side plus cx squared. So this is actually a circle. Divide all sides by c. So we'll get x squared plus y minus 1 over 2c squared equals 1 over 4c squared. So this is a circle. These are circles with a center of 0, comma 1 over 2c and a radius of 1 over 2c. So remember, before we had these circles that were tangent to the y-axis. Remember? They're getting closer and closer and closer and closer. Well, when we go to draw the orthogonal trajectories, they're going to be circles, but their centers are going to be along the x-axis. Let me get a different color so it's more visible. Sorry, they're going to be, these circles are going to be tangent to the x-axis. Right, because the centers are going to be 0, comma 1 over 2c, and the radius is 1 over 2c. So these are going to be circles that are always going through the origin. So it's pretty cool. Now, overall, just to recap, this was a super long example. Super long. Still, 2 basic steps. Step number 1, find a differential equation for the given family. So this is step number 1, right? And the key thing here is you're going to use implicit differentiation, and you're going to eliminate, you're going to have to at some point eliminate your variable, like we have here. We needed to eliminate k. And then step 2, you're going to have a brand new differential equation, and you're going to need to solve that differential equation. For the first example, we used separation.
10 hours.
Thank you. Separation of variables. And for this example, we used substitution, but even though it was long, you just have to keep track of each step that you're doing and make sure that your algebra and your derivative and your implicit differentiation is correct along the way. All right, that's it.